now let's try to put it all together. Okay? Rewind to the beginning of this section. What we started with was a matrix A. That matrix was Hermitian, so it could be complex valued. Okay. Our first step was to say, let's compute a whole bunch of Householder transformations and use these to apply unitary similarity transformations in order to make this matrix into a tridiagonal matrix. So what do we have? We have a bunch of Householder transformations that we apply from the left and from the right. And remember that Householder transformations are their own Hermitian transpose. So this is just this. And and maybe m-1 or m-2, whatever. I think it's m-2. That's how many there end up being, but detail. The result of this is our first matrix to which we apply the tridiagonal QR algorithm. Now, the result of this is actually a tridiagonal Hermitian matrix, and then there's a little bit of a post process that happens to make it into a real valued tridiagonal matrix, but let's not get into that little detail. The important thing here is that this operation right here, if you do it right, is an order m cubed computation. And the details of how expensive it really is, those were in the first unit of this section, where we discussed the details of reducing to tridiagonal form. Now, what one then actually does is the following. One forms explicitly this matrix Q. Okay. Now, notice, all we have is a sequence of Householder transformations. Householder vectors can be stored as part of the process of reducing it to tridiagonal form. We can then take those Householder vectors and apply the algorithm that we discussed back in, I think it was week 3, in order to come up with this matrix Q.